Welcome, everyone. It's great to see everyone today. For today's HPL seminar, we'll be hearing from Dr. Robin Trama. Dr. Trama is currently a postdoc with Dr. Darren Stefanishin here at the University of Calgary. Prior to coming to Calgary in September of 2021, Robin completed his PhD at the University of Claude Bernard-Lyon in France. His degree was in kinesiology, and he studied vibrations in sports practice. His current research interests include soft tissue and muscle vibrations during sports practice, and the effect of equipment in sports performance. His proudest accomplishment is creating a GitHub library, as he was very excited to see others using functions he created. And as a reminder, I'll first turn it over to Robin for his presentation, and then we'll have the question and answer period to follow. So with that, Robin, you're welcome to start whenever you're ready.
Hi, everyone. Thanks, Emily, for the introduction. You should be able to see my screen.
Perfect.
So as Emily said, I will talk about soft tissue vibrations and towards the estimation of muscle vibrations based on ultrafast, ultrasonography, and artificial intelligence. So I'm doing my postdoc here since September with Darren Stefanishin's team. And so I got this project of muscle vibrations, and I'm working on testing some different equipment and sport performance. And I was able to be here thanks to HiHi's and WeTrack program grants. Before coming here, I did my bachelor and master degree in training and performance optimization and my PhD on soft tissue vibrations. So the lab is located in Lyon in France. And the name of the lab was Inter-University Laboratory of Human Movement Biology. So my PhD was entitled Characterization and Study of Vibrations in Sport Practices. I got fundings from the European Union and to do a project with different industrial partners, making sport equipment like running shoes, tennis rackets, or gymnasium code construction. And I would just like to thank my two supervisors, so Christophe Rocher and Johan Blasch, because I won't be here if it wasn't for them. So thank you, guys. So I studied vibration, and it's a topic that was really trending and really a topic that interested sport companies. Mainly because in France, you got a lot of runners, about 12 million, and about 4.5 million team and racket sport players. And we know that there's a lot of beneficial aspects of doing sport practices for cardiovascular perspective or mental or well-being, and also because it increases bone and muscle resistance. But there's also some drawbacks like muscle pain, muscle damages, muscle injuries. And the main cause of that is mechanical stress that is too important. So mechanical stress during sport practices are characterized by the ground reaction force, mainly the impact peak. So this is the first peak after the impacts, for instance, during running, and also the vertical loading rate, which is the rate of force development. You can also add the muscle activations and the muscle contraction that can increase the bone stress. This is not something I will talk about today, but it's good to know that the muscle contraction can increase the bone mechanical stress. And as described by Zadpour and Nikoyan, you can also add soft tissue vibrations initiated by the impact. So after each impact, you got a vibration at the soft tissue level. So we're talking about soft tissues, which are composed of the muscle, but also the subcutaneous fat and the skin. During sport practice, you can have two kinds of vibration. The first one are continuous vibration. I won't talk a lot about this kind of vibration, but it is good to know because you can highly control these kind of vibrations by controlling the magnitude or the frequency, and you can vibrate the whole body or only one muscle with localized vibrators. So there's different studies using continuous vibration show that vibrating muscles under 30 Hz can increase the joint range of motion. With frequency between 30 and 80 Hz, you can create muscle damages, you can increase the oxygen consumption, and you can increase the muscle activation for the same exercise. So you are losing in efficiency. And at last, if you vibrate a muscle between 80 and 120 Hz, you can generate fatigue by central aspects by exciting some afferences. So it's more a central fatigue. The kind of vibration we'll speak mainly about today are transient vibrations. So vibrations initiated by an impact between the foot and the ground. And we don't know a lot of things about this kind of vibrations. So some studies show that if you reduce the vibration magnitude, mainly with compression garments, you can decrease the central fatigue after running on a treadmill without affecting the muscle component of the fatigue. And secondly, if you're reducing the vibration magnitude, you can also reduce the muscle damages 2 and 3 days after your exercise. So we can grasp a link between the vibration and these two aspects, but there wasn't clear correlations or a protocol that shows there's a direct link between vibration and fatigue and damages. Another thing that can possibly explain that is that we are looking at a muscle phenomenon and we are quantifying soft tissue vibration, and maybe we can't access what's happening at the muscle level. So if we're looking at the model of Nikuyan and Zadpour with a ground reaction force model, lower limb model composes different masses and stiffness and viscous dampeners, and the trunk is of less interest for us today. You can see there's a shockwave propagation between this ground reaction force toward the lower limb soft tissues. So we got this propagation because the frequency of the impact is close to the resonance frequency of the soft tissue. And with resonance effect, our soft tissue will start to vibrate. So there's a transfer of energy between our impact and the vibration under the form of a mechanical wave, which is mainly characterized by an oscillation or vibrations. So you can see here basically a vibration just after an impact quantified with accelerometers, and we can define several parameters from this signal. Firstly, its magnitude with the peak acceleration of deceleration or the peak-to-peak amplitude. This value is related to the force applied on our system, so it can be linked to the constraint applied to our mass. We can also compute the damping of the vibration. So this is exponential decay of the magnitude over the time. And it can give us some information about the stiffness or the mass of the muscle or of our system more generally. And at last, we can also compute the frequency of the vibration, so to have also an idea of the stiffness and the mass of our tissue. You can see on the signal on the left that you can compute the frequency by the time period between two peaks. But if you're taking the time between the second and the third peaks, or the third and the fourth peaks, you can have different values. It's because the vibration signal is composed of different frequencies. So you can see here a fast Fourier transform of the signal showing different peaks at different frequencies, meaning that the signal is multimodal and you can just have one frequency to characterize it. The issues with this kind of analysis is that firstly, you're losing all the temporal information. So you don't know when the vibration is happening. And secondly, you assume that the signal was stationary, which isn't the case, as it is dampened over the time. And so the frequency content change over the time. Recently, we can find some studies using continuous wavelet transform developed by different researchers like Enders or von Channer a couple of years ago. And with this kind of analysis, you can define the vibration in time and frequency. You can find the same information as the fast Fourier transform concerning the frequency, and you're keeping all the temporal information. If we're looking at this map in 3 dimensions, you can see that we can also compute the damping of the vibration, as we can clearly see an exponential decay here. So this analysis is can be used to analyze vibrations and to keep all the relevant information about the vibration. So how does it work? So we got a signal that is multimodal, non-stationary, and Cascara showed us that modes or different frequencies are dampened differently in function of the frequency. So to apply this wavelet transform, you firstly need to choose a Moser wavelet. So I show you here a Morse wavelet family that were defined by Lilly and Holed about 10 years ago. And they are calling this family a super family because these wavelets respect some mathematical characteristics that make them really suitable for this kind of analysis. So once you choose your Moser wavelets, you need to make a convolution between different versions of the wavelets and the signal. So the version of the wavelets are either contracted version or dilated version of the Moser wavelet. And you're applying this convolution, which is a multiplication point by point between your wavelets and your signal at each time. By getting the value of this convolution, you create a coefficient that tells you if your vibration is at this moment at that frequency. And you can create the map I showed you earlier. So during my PhD, so I was working on vibration, and we decided to work on this kind of analysis and try to make functions that can help us to analyze the vibration. So you can find on GitHub some of these functions you can use on MATLAB to compute the coefficient maps of your signal and extract some parameters as main frequency, median, and mean frequency, and also the damping coefficient of your vibration. Whether this analysis isn't perfect, you got to compromise between your time resolution and your frequency resolution. And depending on the mother wavelet you choose, you can have maps that are more accurate in the frequency domain or more accurate in the time domain. So it can change how you can interpret your vibration and your signal. So you need to choose carefully which kind of mother wavelet you want. So once we develop this analysis, we were, okay, it's cool, we got maps of our vibration, but how do I know if my vibration before my race was the same than after? And if they are different at what times, at what frequency? So we got a lot of information to these maps, and we didn't want it to lose all this information by just saying there's this peak magnitude or this peak frequency. We wanted to keep all the information in the maps and try to analyze them. So we look at the work of Todd Pataki, who developed a package called statistical parametric mapping, or SPM, in one dimension based on random field theory. He recently had a template to apply this analysis in 2 dimensions based on permutation tests. So this kind of test can allow us to do the statistical inference, meaning that we can find the threshold of significance with our defined alpha risk between our different maps. So this analysis is not new. It is used every day in neuroimaging to define and to find which part of your brain is activated during some tasks. So the idea was really to adapt this method for our vibration signal and our map of coefficients. So if we're looking how this kind of permutation tests are working, I will explain as an example in Nichols and Holmes' article. So you can start with 6 different measures of label A, B, A, B, A, B. And if you are computing the t-test between these 2 conditions, you got a value of plus 945. The idea of permutation tests is to relabel all your measures. And with 6 different measures, we can have 20 possible cases. And the case in the example is the number 6. For each one of these cases, you compute the t value or the f value if you're doing an ANOVA, or the value of your choice depending on the test you're doing. And you're looking at all the value. And we can see here that the number 6 is the highest value among every other one. So that means that there was 1 chance out of 20 to be the highest value, and that there is a difference between A and B at a p-value of 0.05, which is our alpha risk. So this is principle when you want to do that with 1 point, but with our coefficient maps, we got several hundreds or thousands of points, which I will call nodes in the following example. And to apply this method to all the points, you need firstly to compute the distribution of permutation at each node, and then choose the node with the highest value from all permutations. when you find this node, you can rank all the t-values. So I'm taking an example with 100 permutation, so with a maximal value of 10. And you can see the 9 first value and the last one. We need to select the first value below our alpha risk. So we got 100 permutation and a risk of 5%. So we need to choose the fourth value and use the corresponding t-value as our threshold. So it's 9.3. Now, all nodes with a t-value above 9.3 or below minus 9.3 if we are doing a two-tail t-test are significant. And that's how you can define a threshold for your map and define which nodes are significant and which one are not. There is also some drawbacks to this method because you can't have a precise p-value under the threshold in 2 dimensions. You can have that in 1 dimension with the different clusters, but the non-parametric approach doesn't allow you to do that in 2 dimensions. There's also a link between the number of permutations and the accuracy and repeatability of your analysis. If you're doing only 100 permutation on 1 million possible, if you're doing that for one other 100 permutation, you can have a different threshold. So the idea is to increase the number of permutations to be as close as possible from the real distribution of your statistical test. And at last, when you are doing post-hoc tests, this method doesn't assume a global smoothness of your data. So it can lead to minor differences with a real post-hoc test. We also coded this analysis on MATLAB and published an article with it. And basically, this function can help you to do analysis of variance and post-hoc test for 1D and 2-dimensional data. So these two kind of analysis, so signal analysis with wavelet transform and statistical one with statistical non-parametric mapping really helped us to quantify and analyze vibrations, and also some different biological signals that are often during human locomotion, non-stationary and multimodal. For instance, we investigate the effect of fatigue on EMG data. We also use it to quantify EEG signal depending on the activity performed by our participant. And we use the 1-dimensional analysis to evaluate the effects of injury status on joint torque at different moments after an injury. So it can really be useful for a lot of different applications in biomechanics and physiology. So if you had any question about that or some inquiries, don't hesitate to contact me. If we're going back to vibrations, the idea was to estimate, once we got these two kind of analysis, was to estimate the muscle vibrations. So on one side, you can quantify the vibration with 3 actual accelerometers that are really good to field and lab measurement. They are light and with a great sample frequency. And there's still some things we don't know about this kind of devices, like what is the pressure we are applying on the soft tissue when we try to stuck the accelerometer on the skin, or what is the effect of the cable if there's one. On the other end, you can use ultrafast ultrasound to assess directly the muscle displacement. And the ultrafast technology allows to have videos between 1,000 and 20,000 hertz, with largely enough sample frequency. However, ultrasound is good for lab measurement, and you need to compensate the probe movement during your task. And you also need to have a good tracking algorithm to follow the points on your video. So we got on one side a device that can quantify the soft tissue vibrations, and the other one the muscle vibrations. And in one of our study, we try to compare these two devices to see if accelerometers can really assess the muscle vibration, and if it can't, what is the cause of its inaccuracy. So to do so, we recruit participants with large differences in fat thickness from 4 to 18 millimeters. And we use the same impactors used in the study of Wackerling in 2001. So we induced a shock on the lateral side of the thigh, and we quantified the vibration of the vastus lateralis muscle with either accelerometers or ultrafast ultrasound. We quantify this vibration in 2 axes, and we also control the level of muscle activation. So we did this experiment for a relaxed muscle, and vastus lateralis contracted at 40% of its maximum. So as you can see on this little video, the probe was stuck in a probe holder to be out of contact with the skin. And we control the level of activation to be the same between our 2 devices. And we also control that the vibration was not or minimally transferred to the probe. Once we got our ultrasound videos, so the videos I will show you are slowed down by 100 times, and the green points you can see on the first image are the features we detected with brisk algorithm. And using filtering, averaging, and derivation, we went from the average displacement to the average acceleration. And you can see for a contracted muscle now that the vibration is at higher frequency. And you can also see that we have lost some points during the tracking because the video was too fast even for 1,000 hertz. So with this acceleration data, we use our wavelet transform to obtain mean maps of coefficients. And we use the difference between the 2 maps and the statistical non-parametric mapping analysis to define clusters where the vibration was different. So these maps are for a relaxed muscle, and these ones are for contracted muscle. So we use an analysis of variance and post-hoc test to define our different clusters. And so on the bottom maps, you can see the cluster A on the left, depicting that the accelerometer underestimated the magnitude of the vibration above 50 hertz at the start of the vibration, so during the first 0.05 seconds. And on the bottom right of the map, the yellow color show that the accelerometer overestimated the magnitude of the vibration under 20 hertz, and especially after 0.1 second. The other cluster, B1, was of really low magnitude. So we considered it like just a difference in the electronic noise caused by the accelerometers. We also did some correlations between the relative differences between our two devices and the fat thickness. So for the damping property on the left and the median frequency on the right, we show that more you are increasing your fat thickness, more the accelerometer is underestimated the frequency and the damping of the vibration. So we conclude that the accelerometers capture only the salient characteristics of the muscle vibrations, and it was really depending on this fat thickness. So we made some suggestions to better capture the muscle vibration with accelerometers. Firstly, we can select participants based on their fat thickness. So the thinner they are, the better it is to access the muscle vibrations. If we need to compare different populations, we need to quantify the fat thickness under each accelerometer, because difference between two populations can be due only because their fat thickness are different and not because the muscle vibrations are different. And at last, if you're looking at the map on the bottom right, you can see there's only few vibration magnitude under 20 Hertz. And this is mainly the frequency that are amplified by the accelerometers. So we also suggest to high pass filtering the signal at 20 Hertz. So trying to remove what's happening under 20 Hertz to better assess the muscle vibration. So this is not perfect because there's also some frequency that corresponds to muscle vibrations, but it can be a step to be closer to this kind of vibrations. This study was really interesting for us on many aspects, but inducing a shock on the lateral part of the thigh is really different than an impact during running. It's not the same location from the impact. During the stand phase, you got movements caused by the joints and the muscle, and you also got some muscle activation patterns that are different from an isometric contraction. And at last, we quantify the vibration in two axes, but we need to quantify this vibration for a third axis too. So we look toward what is done from different companies, and you can see that you can use ultrasound during walking and running on treadmill by holding the probe on your muscle and putting some reflective markers to track the movement of the probe over the time. So we start with this idea to quantify the muscle vibration during walking and running. And we wanted to add also inclination to have a lot of different conditions to compare the soft tissue vibrations and the muscle vibrations. For this study, we'll need to do our measure on two separate times. So as it was shown by Boyer and Nig, the vibration is dampened inside the muscle. So if you're not at the exact same location, the vibration can be different. And we also need to do different measure with ultrasound, because if we want to assess 3-axis muscle vibration with ultrasound, we need to rotate the vibration by 90 degrees to have the three axes. In addition of these measures, we need to assess some biomechanics data like kinetics and kinematics, and also muscle activity, and also assess some muscle or soft tissue characteristics like the muscle rigidity, the fat thickness, of course, and the muscle mass or PCSA. The idea of these other parameters is firstly to be able to correct the probe movement during the stand phase and to apply rotation and a translation to the ultrasound videos. As we need to do separate measures, we'll need to match the different impacts that are the more likely to cause the same vibrations using, for instance, K-means clustering or some artificial intelligence clustering. And at last, we can use this muscle or soft tissue characteristic to drive our machine learning model. Because in the end, the idea of this study is to transform our soft tissue vibrations into muscle vibrations. So to be able to characterize the muscle vibrations with an accelerometer, simply by giving the algorithm some basic information about the muscle mass, the muscle stiffness, if we can, and the fat thickness. So we'd like to use a recurrent neural network and having this kind of information as input to obtain our muscle vibration as output. The idea is to use a long short-term memory neural network. So this kind of network was really recently used by Ryan Alcantara to translate, like language translation, data from IMUs to ground reaction forces. The idea is to use the exact same technique to translate our soft tissue vibrations into muscle vibrations. So we tried, so I've been here for a couple of months and I tried to set up and to analyze some data. So you can see here a video during walking. So the video is only 2 seconds, so it should last 28. So it's slowed down by almost by 10 times, a bit more. And so you can see our tracking algorithm was a bit modified, and the different colors are corresponding to different tracking algorithm, because when we are losing some points, we need to retrack new ones. So this is not perfect because we are losing a lot of points, and it's really hard to compute the acceleration of our muscle with points like that. And the second thing we do is to 3D print a probe holder to be able to track them with our Vicon cameras. The other idea, if we can't track muscle vibrations with this kind of algorithm, we can use a point distribution model, which was used by Lai and Hodson 2 years ago. So this kind of analysis is based on the fascia of the muscle and relied on a lot of different points. The only thing is we can only have the transversal axis motion, and it can be a start, but it won't be applicable for what we want to do in the end. To just finish this presentation, I'd like to thank the Darren's team for their welcome since I'm here, and for their help, and leaving the sound and mic to Emily again. Thanks for your attention.
Thanks very much, Robin. At this time, I'd kindly ask you that if you're comfortable, to please turn on your Zoom camera to allow for a better discussion. To ask your question, you can use the raised hand function under reactions. And if you're unable, you can type your question in the chat box and I will read it aloud. Amin, please start us off.
Okay, my question is about slide 25. You showed the like the testing setup that you have. You had like your ultrasound and the accelerometer, and you just like vibrated the muscle at a point. What I see in that slide is that the distance or let's say it this way, the accelerometer was at a farther distance to the point that you hit the muscle compared to the ultrasound probe. And when we talk about vibration, vibration is a mechanical wave that propagates, right? So maybe the wave that reaches to the accelerometer attenuated a little bit. So that's the reason maybe why your accelerometer underestimated some of the frequencies. Isn't it the case?
It's something we thought about. So yes, the impact was on the side of the thigh. So it was clearly, the muscle was closer than the accelerometers. I don't know if it's the fat thickness can attenuate the higher frequency as the wave travel through from the muscle to so through the fat, then to the accelerometer. The fact is, the vibration was also initiated to the skin and travel also directly from the impact to the accelerometers, and not going specifically through the muscle then to the accelerometers. So I don't know if it's just because the fat attenuates how the vibration between the muscle and the accelerometers, or if it's just because it vibrates at lower frequency than the muscle, because it has a lesser stiffness.
Mm-hmm. Okay, thank you.
Arash, please go ahead.
Hi, thank you for great presentation. So I have a couple of questions. The first one, so I'm just looking at the frequency of the vibrations specifically. Like, we see frequencies well above 50 hertz. And so for example, in running condition, the external force that probably produces those vibrations is around like ground reaction forces frequency is around like 30-40 hertz at max. And where do you think these vibrations coming from, assuming that the input, we know the frequency of the input, and then why the output frequency is such higher than the input frequency in that case?
Yeah. So with the resonance effect, if the ground reaction force is at the same frequency as soft tissue or muscle resonant frequency, you got an increase in the magnitude of the vibration. But if you are vibrating a muscle at a lower frequency at a higher frequency than the resonant frequency, your muscle will still vibrate at the input frequency, but only the magnitude will be attenuated as you go far apart from the doing again. If the resonant frequency of the muscle and the frequency of the input are far apart, the magnitude will be reduced, but the muscle will still vibrate at the input frequency.
Yes.
On this experiment, what dictates our input frequency was muscle stiffness itself, because there's no impact between the foot and the ground on our study. And it's just like a contracted muscle has a stiffness way higher than we can have during running, or I don't really know if we will have such high frequencies during the running study, for instance.
Yes, so you're talking about this impact study, right? The one
Yeah.
that so do you have any idea what the frequency of the impact was specifically?
No, we just have the vibration data, but the impact was initiated directly on the muscle. So the input frequency is the vibration frequency in that case.
Okay. Yeah. So another question is, basically, I think I did some studies on soft tissue vibration as well, and I always had this question of increased vibration. Is it good or bad? I'm not quite sure.
Yeah, I would say it's bad because you can, like any mechanical stress, if you increase too much vibration, you can have some negative effects. But if you're not training with vibrations, you might you might lose some adaptation and not be as performant as someone training with vibration. So depending if it's a training session or a competition, I think you should try to, in one case, to keep the vibration like a training stimulus. And in other cases, like competition, you want to reduce them to maybe, and I say maybe because we don't really know the effect of transient vibrations, maybe limit the muscle fatigue and muscle damages after the competition.
Yeah, nice, thank you.
Tim, please go ahead.
Yeah, thank you for the interesting talk. So I did some research on soft tissue dissipation, which is related to, but slightly different. So I'm not super familiar with vibration. Can you maybe talk a little bit about what the applications are in terms of maybe injury prevention? So is vibration a good thing? Like if you know perfectly your vibration, what are you gonna tell the athlete?
Yeah. So more than the athletes, I think the targeted audience is more sports companies making equipment. Right now, most of the companies I work with want to reduce vibrations, and they don't really know what kind of frequency they need to limit. We can say, okay, we need to limit the higher frequencies of vibrations because it can cause muscle fatigue, muscle damages, and etc. But the fact is, we don't know at which frequency the muscle is vibrating. So we first need to isolate the muscle vibration to better understand how an equipment can act on this kind of, so on the vibration and on the outcomes after an exercise, for instance. And
is the idea mostly that you want to apply vibration to stimulate muscle growth, let's say, or is it more like you want to reduce vibration to improve your movement, let's say?
Yeah. The main idea is to reduce vibrations to improve athletes' risk of injury and fatigue, and not using vibration as a training modality.
Okay, thank you.
Benno, please go ahead.
The mic is off.
Can you hear me now?
Yeah, it's good.
Sorry. In this context, I'm wondering whether it is really a question of injuries or it is much rather a question of performance. You know, if the vibrations demand more activity from the muscles, for instance, then that would mean you have more fatigue and at the end you have less performance. So I don't think it's a question of injuries, it's a question of performance on.
Indeed, it's just maybe too much extrapolate to go on the injury side. And yeah, firstly, we can target muscle performance and fatigue, but there's also a link between fatigue and risk of injury. That's why I talk about injuries, but mainly, yes, to improve performance and limit fatigue.
Now I have another question. You said the true vibration. How did you determine the gold standard?
So yeah, the ultrasound was defined as a silver standard. We don't have really a gold standard for that.
But if you say it's wrong, it's higher and overestimates and underestimates, then you have to compare with the gold standard.
Yeah, but we actually don't have one.
So how do you compare then?
Compare it to our silver standard, which is not perfect, of course, but it was the best we can do, and with the actual technology, I think this is the best we can do. Or if you have some insights or of other devices that can assess muscle vibrations, I'm glad to hear that.
I don't have any.
Yeah.
And when you said overestimated and underestimated, how much did you think is they overestimated? And is it 5 hertz or 50 hertz or?
So if I just, we were between 10 and 30%. So for
10 and 30%,
around 20-30 hertz, it's between 5 and 15 hertz.
Yeah. Thank you.
Yeah, you're welcome.
I'm going to read a question from the chat. So if I understand, this is from Matt Corwood. So if I understand, high frequency vibration was not good for the body, but was there a conclusion if vibration is worse for tendons or for the muscle?
I don't have an answer for for this question. There was one study that investigates the tendon vibration, and they kind of find out that the vibration was at almost the same frequency than for the muscle. But yeah, I can't tell if it's better or worse in terms of structural modifications, because yeah, the bad thing for the muscle is the muscle needs to adapt its contraction to dump the vibration, but tendons are passive structures, so they don't have this kind of issue. So I would say it's more, it's worse for the muscle than the tendons, but I don't have a clear answer.
Great, Brent, please go ahead.
Thanks, Robin. You showed two findings that I thought were kind of interesting. And the first one was when you do the continuous wavelet transform, there were frequencies in which the accelerometer or the IMU overestimate was higher than the ultrasound. And then there were other frequencies where it was lower than that. There was this guy once who did this experiment where he had a 2x4 in a water bag, and he tied an accelerometer around the water bag, and then he screwed the accelerometer in the wood, and then he banged it into the ground. And do you know who that is, Benno? Do you know who did that study? Anyways, And it showed that depending on the input frequency, sometimes the accelerometer on the water bag could over predict what the acceleration that the wood experiences, or sometimes it could under predict. So, but I don't know if that's what's going on with your experiment. So have you thought about like why for some frequencies the IMU is over or is higher than the ultrasound machine?
I think the main cause is because the fat tissue are have a lesser stiffness than the muscle, and so the fat is vibrating at a lower frequency during a longer time than the muscle, and so we got these accelerometers vibrating at lower frequency during long time compared to something at higher frequency and for a shorter time. So if we are looking at the maps, we can see that the vibration quantified with ultrasound is located on the top left of the map. And for the accelerometers, it's more in the middle. And so there's kind of a crossing of the amplitude value with higher on the top left for the ultrasound and higher in the bottom right for the accelerometers.
Okay. I think I understand. So there's just kind of like, there's two frequency bands for one for the ultrasound and one for the accelerometer. They're sort of shifted a bit in the frequency space. And so one has to be higher at one point and the other one has to be lower. Yeah. Okay. All right. And then related to that was this, and I apologize if somebody asked this question already, but there was a nice relationship between fatty tissue and the relaxed vibration. But then that relationship went away in the contracted condition.
So there was this relationship.
Sorry, with damping.
Yeah, just for damping. Yeah.
Right, not with frequency. It was still there with the medium frequency, but it was there for damping. So what's going on there?
I don't really know why damping was totally different when the muscle was contracted.
Well, it almost seems like the damping itself that you measure is due to like the inertia of the muscle mass. And when you contract it and you take that out of the equation, all that's left is fat tissue, and it doesn't really dampen the signal very well.
That's not wasn't dampened. It's just that the differences between our devices cannot be explained by the fat thickness.
Okay. And then, do you know if I should think of this as for the people with more fat? Do they have more muscle too? So should I think of them as having sort of the same like proportions of lean mass and fat mass, or were you able to measure if the lean masses were different between the groups?
It's hard to tell because at first we were okay. If we got more mass, we should have a lesser magnitude as it for the same impact. If we got more mass, the acceleration should be lower. And the fact is we got more magnitude at the quad than for a calf muscle, for instance. So it's further from the impact, and it's with a bigger mass, but the acceleration is still higher than for a smaller muscle closer to the impact. So I don't really know. For an isolated system, this relation between acceleration is mass and force is kind of clear. But for a muscle or just a part of the muscle, it's not that clear. And I'm not sure people with more fats have always more muscle. I think it could be really interesting to have both values. But,
thanks.
Yeah.
Walter, please go ahead.
Yeah, just coming back to the previous question there, I think the simplest explanation why in the active and passive case the damping is different is because the stiffness of the system is different. You know, because you can have essentially three modes: overdamped, overdamped, or critically damped. Mm-hmm. And part of how the system behaves depends on the stiffness of the system. And we know from basic muscle mechanics that the stiffness dramatically changes when a muscle increases its force. So force and stiffness are essentially parallel, with stiffness preceding force by about a millisecond or two because of the weakly bound cross bridges. And I guess that brings me to my general question: how do you account for that? For example, you're saying that you want to determine the stiffness of the muscle, or that the muscle behaves is excited as a resonance frequency, but the resonance frequency depends on the stiffness of the system and therefore of the muscle. And depending on what you read, people argue that the stiffness of a muscle from relaxed to fully active changes by a factor of somewhere between 100 and 10,000. So you have this enormous change. How do you account for that when you do those type of analyses?
So link between the stiffness and the frequency are so this is a ratio from the root mean square. So you say there's an increase 100-fold. The frequency might be like 10 times higher. So even that doesn't make sense because we don't have frequency at 130 hertz for peak frequency. So yeah, there might be something else. And I don't think the kind of simple equations between stiffness and frequency we can find for an isolated system can be applied at ease for muscle, which is way more complex than just an isolated system. And we don't have also access to the entire muscle and just a small part driven by the size of our accelerometer or the surface of a probe. So it's pretty hard to, I don't have the real answers how we can account about this kind of differences.
There is also an area of research called vibromyography, where people measure muscle vibrations, and some of these measurements are done on the perfectly isometric, non-moving conditions, no external force, nothing. And then you can measure very distinct vibrations of the muscles as it's activated, even without any movement or any perturbation. These are, I guess, not visible except if you have very fine measurements of lasers that go back on muscles. And so do you consider those at all, or how would those vibrations fit into those big vibrations that you seem to be looking at, or can they be neglected?
No, I never considered this kind of study on isolated fibers.
I was just thinking, because you talk about energetics and that energetically might not be good for the muscles to vibrate, but we know that muscles vibrate when they are activated, even without you doing any perturbation to them. I was just wondering if that plays potentially a role. The other thing that I was interested in is that you said, you wanted to look at muscle vibrations, and the study was motivated by looking at the energetics. But wouldn't you think that it's important to also look at the fat tissue and other tissue vibrations than just the muscle? Or do you think that the muscle vibrations would be the primary determinant of loss of energy, and fat vibration or other vibrations might not be really a contributor to an increased energetic demand that you need to have due to the vibrations?
I think the muscle is at the center of everything. This is thanks to muscle you can move and you can damp the vibrations. So I think the fat doesn't have any role in this kind of energetic or damages and other outcomes. And the other thing with muscle activation is, for me, we are not even sure that we increase the muscle activity, because there was one study during biking. They just use a filter to remove the acceleration data from the EMG, and they showed an increase of 0.05% on the EMG data. So I don't know if it's just an artifact of the vibration on the EMG signal, or if there's really an increase in the EMG. So the result for oxygen consumption are clear, because I don't see how vibration can change VO2 values. But for the EMG, I can have some reserves.
Then the last question I wanted to ask is, you said that in your tracking algorithm that you're using now, you're losing points a lot.
Yeah.
And you wanted to do it three-dimensionally. Would that require that you needed multiple ultrasound probes on the same muscle in order to do that? And has anybody ever tried to do that?
So the idea right now is to do the measure at 2 different times. So there will be 3 times in total, one with the accelerometer, one with a probe in one axis, and a third one with the probe in the other axis. And that's why we wanted to quantify the kinematics and kinetics data and muscle activations for each impact with each device, want to match the impacts that are likely to cause the same vibrations, meaning with the same ground reaction force, the same joint angle at landing, the same muscle activations, for our 3 devices or for our 3 measures to be as close as possible to have the same vibration.
If I were you, I would try to make those simultaneously rather one after the other. That might be a little bit complicated, but that would be really cool. Yeah. To have multiple probes on there to really see what might be happening 3-dimensionally. Anyway, thanks a lot.
Yeah, but it could be really nice, but we need to be at the same spot, because the vibration magnitude is dampened as you're going in the proximal or distal part of the muscle. So if you're not at the same position, you can have different vibration characteristics.
Okay, so yeah, that makes sense. Yeah.
Spot, yeah,
that makes sense. Yeah.
Robert, please go ahead.
Robin, you've got vibration of your muscles and you've got vibration of your tendons. And so you've got vibration of muscle spindles and vibrations of Golgi tendon organs, which are giving feedback. And so if you're running, I've always thought motor control to be incredibly forgiving. But if you're getting vibration signals onto those receptors and going back into the feedback path, so when you go from running on nice soft green grass and then suddenly you step across onto the footpath, which is concrete, and you get more vibrations, your motor control, I would imagine, is getting swamped with this new signals from the spindles and Golgi tendon organs, and then you get back onto the grass with the next step, and you've got to sort of compensate for that. Have you given much thought for, apart from the mechanical tissues, to the influence on the neural tissues? Because you're talking about not much change in the EMG, but you could argue why you could see a change in the EMG. Have you got any thoughts?
Yeah. So when I was saying, when I was talking about the change in EMG, it was just with imposed vibration during cycling. And there was this study here in Calgary by Bowie in 2006. They changed the surface hardness without telling the participants. And when it wasn't aware, it will change the from go to grass to hard ground. There was no modification in muscle activation, but an increase in vibration magnitude. But as soon as the person was aware, it will change. You have a change in muscle preactivations, joint angle, joint stiffness, and the vibrations stay at the same level. So that was basically what's explained by Beno Nig and the muscle turning paradigm with all this kind of study how the muscle preactivation and activation are modified to keep the vibration at a low level.
So you think the central nervous system took that information and as a feed forward system altered the pathway next time it met it?
Yeah, so for if the person was not aware about the change of surface, the first stand phase won't be modified, but the next one will be.
Yeah.
And so yeah, it's kind of feed forward, but it's something from the muscle, but also from all our sensors. Because if we see, we will change and going from grass to hard ground, and we in the past already experienced running into hard ground, will automatically adapt our running pattern.
Right.
And we don't need this first impact to adapt. We already know how to do that. We just need to be aware we need to.
Thank you.
Benno?
I assume that you modeled the input force as a vibration, correct?
As a
sinusoidal.
We just quantified the magnitude of the passive peak and the frequency of the impact and the vertical loading rate, but we didn't model it with different frequencies.
But I mean, in reality, it's a shock that you have.
Yeah.
And if you consider that as a shock, would your application be different?
Yeah.
Because the shock doesn't have the frequency problem.
The shock doesn't have to be what, sorry?
Doesn't have the frequency problem.
Yeah, we use often an accelerometers on the heel cup of the shoe to find also this kind of input frequency, so more like a shock. But yeah, I don't know for the run reaction forces.
I would look into that.
No, we haven't looked into that. I don't. Yeah. I don't have answers for this question, sorry.
Okay, thank you.
Arash?
I just have a very technical question. I think I saw it in one of your papers as well, that you use the specific wavelet function, the Morse wavelet, if I'm not mistaken. And I was wondering, like, if I'm not mistaken, in some other studies, they use the Cauchy type wavelet, and then they optimize it specifically so that the difference between the center frequencies is enough that you have basically, it's larger than the, the frequency resolution of Fourier transform.
Yeah,
and I was wondering why you specifically chose this wavelet, and with, I think it was like 25 different wavelets there. with a very close center frequencies.
Yeah. So yeah, at first we use the Cauchy wavelets. It wasn't really efficient. It was really long computation time, and it was there was great differences between each variation of the wavelets in the shape of the maps, and we were not really happy with that. But I did that in my master degree, and I wasn't really at ease with all this stuff yet. And so we choose the MOS wavelet because it's defined as a kind of super family of wavelets. And one of the characteristics of the MOS wavelets are they are analytic wavelets, meaning if you have a signal, a sinusoidal signal of amplitude of 2, the wavelet coefficient will be 2. So you can find the exact magnitude of your signal with this kind of wavelet. The other thing is, as you said, is the frequency response of the wavelet. So we use, so I'm not a mathematician, and I don't really know how they applied that to their the filter bank of wavelets, but it's not depending on the number of wavelets because they are spacing and modifying the response of all wavelets in function of all the wavelets in the filter bank. So it's not like 7 individual wavelets like it was done by von Channer. It's a filter bank is like a whole. So, and every computations depend on the entire filter bank. So if you got 30 wavelets, or if you want to increase the resolution and you got 60 instead, the computation isn't the same, but the result in terms of magnitude will be the same.
Yes, that was basically the main reason of my question. Then, for example, Anders and colleagues use 13 wavelets. Yeah. And then here you use 25, and assuming that, well, basically should give you the exact same amplitude, no matter how many frequencies you consider. But when you consider more frequencies, two things come into account. The first one is that the center frequencies become so close together that might be smaller than the resolution, the frequency resolution of the transform specifically. And the second thing is the computational power. Then doing 25, like convolving 25 wavelets is much more computationally cost effective, not cost effective than the other one.
For the computation time, wavelets created by Lily and Olet are kind of effective. I never had an issue with really long computation time. And the idea behind using a lot of wavelets, so the frequency are logarithmic scaled to allow a regular response, and have for each frequency the same amount of the original signal. And using more wavelets, which are still scaled but really closely, is to interpolate the frequency by 1 or 0.5 hertz, and have a map that is just scale linearly, and to be easier to interpret. That's why we use a lot of different wavelets. It's to try not to fill too much gaps between frequency, and especially for higher frequencies.
See, thank you.
Yeah. Great. Maybe I'll ask the last question. Robin, if high frequency vibrations are bad for injury or performance, what are some intervention options for attenuating that besides compression garments?
Some studies show that increasing the shoe sole stiffness can reduce the vibrations too. But it was really extreme, and I don't think we can use this kind of shoes for running and stuff and being performant at the same time. You can also change the floor construction. Recently, we tested a floor with a decreased horizontal stiffness. So when you're striking the ground, your foot will just slide on the lateral side or anteroposterior axis, and you can decrease the impact with that. And recently, there was a study here in Calgary showing that it's kind of the same if you increase the horizontal stiffness, if you decrease, the horizontal stiffness of the shoes. So it can be another thing. For a long time, we focused on the vertical stiffness, trying to dump and play on the thickness of the insole or its hardness. But recently, yeah, some study shows that maybe playing on the shear stiffness might be more effective.
Great. I don't see any more questions. So Robin, thank you very much for your presentation. And thank you to all the audience members for your questions and the discussion. Next week, we'll be hearing from Joel Burma, advised by Dr. Jonathan Smiro. And I hope to see everyone at the seminar again next week. Thank you.
Thank you, Emily.